Sorry about the slight delay. This was because I seemed to have lost the Zoom icon on my panel. So took a little while to figure out how to start even the Zoom meeting. Okay, so yeah, towards the end of last lecture, I was talking about product, product and completion. So, so let me recall for you very quickly. So suppose that this is about products. So we'll come to completion in a few minutes. Suppose omega 1, F1, P1, and omega 2, F2, P2 are probability spaces. Then we form the product. So omega 1 cross omega 2. So G of F1 cross F2 and P12, it's written as, okay, P12, all right, where we form the product probability space. So, so the main thing is G. So where G F1 cross F2 denotes the smallest sigma ring or sigma field, whatever, sigma ring generated by F1 cross F2, okay, which by definition, as you will recall, is just pairs of spaces A1 cross A2, where A1 is in F1 and A2 is in F2, okay. And as I was saying last time, this one has to make this first because recall that F1 cross F2 is not a sigma algebra, sigma ring in general, yeah, most of the time. Well, okay, let me say in general, okay. For finite things, there's no need to worry. But when F1 and F2 always contains singletons, then it's okay. But in general, particularly when you have infinites, omega 1 and omega 2, and singletons are not necessarily the most interesting ones, then this will be problematic. Yeah. So this is a situation. It is not a sigma ring in general. So as I was remarking, F1 cross F2 is not even closed under finite union. So you just have to remember, so it's not closed under, it is also not closed under complementation. So as I was drawing the, sorry, so this, let me draw a proper figure of it, and you will see immediately why it is not. So you see a product, something like this, and then you can have some set, okay, product of this small interval type of thing and this small interval. Then you get something like this. Okay. So this is the interval that you will get then as product. Okay. But its complement is not a product. Okay. And I can have also, it's not closed under union, because if I just have another rectangle like this, say something like this union is also not a product. Union of red region and the green region will not be product of just two sets. You can just easily verify it by assuming that it's product of two sets. Then the individual sets B1 and B2 can be obtained by just projecting the sets to the horizontal and the vertical axis. So this is a basic problem. It's not closed under complementation. So the thing is, as I was saying, again, let me just reiterate this, because these are new concepts perhaps for you. Mm, uh, there exists always a sigma algebra. So if you are given any omega, not necessarily looking like a product or something, suppose I have some omega. So given omega, this is also just a remark aside. Given omega and a subcollection F, so a collection, not Y subcollection, a collection of subsets. So contained in so script P of omega. This is subsets of omega, okay? Not to be confused with probability or anything like that. Then F is contained in a sigma ring, namely, so namely I can just take this omega itself. Once this happens, then taking intersection of all sigma rings of omega, which contain F, we obtain a sigma ring again, because intersection of arbitrary collection of sigma rings is again a sigma ring. So we obtain a sigma ring, which is what we denoted script G of script F contain F. This is the smallest. This is the smallest sigma ring in a omega that contains F. Contains F. So you see, therefore this definition is now complete. And P12 again recall. So recall. First of all, P12 on product space, I may have just called it P. It doesn't matter. P equal to P12 is completely determined by just prescribing it on the generating collection. So P1 of A cross A2. This is equal to P1A times P1 P2 of, so this is P1 of A1, P2 of A2. Okay, so in this thing, note that. So again, I have some remarks to make. Note A1 cross A2 is itself an intersection of two things. A1 cross omega 2 intersection omega 1 cross A2. Okay.
Sir, can you scroll up just a little? Okay, sir. Okay. Thank you.
Yeah. So, and what about P of A1 cross omega 1, omega 2? This is equal to P of A1, P1 of A1. Because, see, if you apply this formula, P2 of omega 2 is 1. Okay. And likewise, the other one also, P of omega 1 cross A2 is also equal to P of A2. And what it says is that, therefore, A1 cross omega 2 and A2, omega 1 cross A2 are independent events. Dependent events. In other words, so you look at the product space and you specify the event A1 should occur, but you are not bothered about what the outcome of the second thing is omega 2. Okay, and likewise this one. So occurrence of the first coordinate being within A1 and the second coordinate being A2 are independent events in the product. So this is the main thing. In particular, uh, yeah. So okay. That, I think this, I don't need to say anything more beyond this. So okay, so we have only defined it on this one, and it's determined by just this, because everything else will involve uh, countable union, countable intersection, and then complement, and so on. So once I know it on the generating set, it's determined. Of course, one has to rigorously prove this, but it follows from how you would actually construct GF. This only proves out of existence, but GF, if you imagine what it would be, it would involve you just saturate your collection by repeatedly applying. It may not be that you just apply it once or twice, you may have to apply it several times, and you do that and you will get it.
Sir,
Yes.
sir, why are they independent? I mean, what if omega 1 and omega 2
Okay.
not?
Omega 1 and omega 2 are total spaces, no? Omega 1 is a probability space on which P1 is defined. See? So if I write P1 of omega 1, that is 1. Omega 1 is an event. Sort of, it's like the universal event for that. If you think of it as possible outcomes of an experiment, omega 1 is the sort of universal set for that. And so probability of P1 of omega 1 is 1 by the axioms that we wrote down for probability, right?
No, no, no. I'm asking why can't omega 1 and omega 2 intersect or something?
No, that because you see the first coordinate never intersects with second coordinate. I mean, so you may say, well, x-axis intersects y-axis, but yeah, I mean, what is so? How do I say this? So you see, okay, let us write. What do you mean by omega 1 intersection omega 2? I can make sense of this only if they are subsets of a bigger set, right? Both are subsets of some set. Okay.
Yeah.
So, but then you may say, okay, I identify omega 1 with omega 1 cross some point y, and omega 2 with something. I identify it with some x cross omega 2. But this is after identification. Okay. In any case, you can identify it all right, but see, these are themselves. See, you must think of omega 1 and omega 2 as two distinct copies, if at all, if you want. Two different um, different probability spaces. What do you mean by whether they are independent? I mean, I don't know.
No, so like when there are two different sample spaces or like probability spaces, I understand. Okay, so the axes don't play like what happens in the x-axis doesn't affect y-axis. But like if omega 1 intersects omega 2, and what I mean is in a bigger space, then
In
what
a
is
bigger space, you will have to identify this, right? You will have to identify. Okay.
okay.
You have to make a choice and then identify, and then also then you see it could so happen that if you identify it, then what happens to p of omega 1, suppose. So this will be p of by definition omega 1 times is a product of real numbers, okay, of this y. But it could so happen that this could be, sorry, this is p1 and this is p2. It could so happen that if you take 1 point sets in omega 2, probability of that is 0. Okay, so it will give you this is equal to 0. So that's if that is what you want. But this is not what I meant here. You see, when you read it very carefully, you have second coordinate is allowed to be free, whatever it is in this set. In this set, let me underline that. In this set, well, in this set, the first coordinate is allowed to be free, and it makes perfect sense to write this. Yeah.
Yes.
So if now when you do this, all I'm saying is you have written A1 cross A2 as intersection of two sets. And by definition, probability of this, I know how to compute it. It is P1 times P2. But on the other hand, I compute the individual probabilities of these two sets, and they turn out to be P1 of omega 1 by the same definition, and P2 of omega 2 by the same definition. So P of, here I should write P2, okay, of A2. And that means that probability of A1 cross A2 is just this. And that what is it? So it's like this. You know this is nothing new. You have seen many examples of this. Think of tossing two coins. Sorry, think of tossing a coin twice. The outcome for, so let me just give this example. Let omega 1 be the outcomes of tossing a coin. So this is of course head or tails. Okay. Now omega 2 is also equal to omega 1, and say the probabilities I'll take, say, and I'm not going to write F1 and F2, they are again the same. And so tossing uh, uh, tossing a coin, probability of head, so P1 of head is equal to P1, P1, P2 of head, let us say is P. And of course, Q is equal to 1 minus P is the probability of tail, okay, in both the experiments. Now, what is omega 1 cross omega 2? Omega 1 cross omega 2. This is, of course, all possible combinations. Head. Sorry about the bad iterate. Head tail, tail, head, tail. Okay, that's it. Okay, and now we say that the outcome of the first toss is independent of the outcome of the second toss. What exactly we mean is, if you are thinking of your probability space as this, H cross omega 2 is independent of, well, you can say either T, I mean, whatever, omega 2, sorry, omega 1, cross, you can write HRT, no problems. Yeah. This is exactly the type. So you are familiar with this, right? Outcome of the first one, if it is head, it has no influence on the outcome of the second toss. So the rigorous way of writing, so you, of course, intuitively we also know how, without bringing in the notion of products, we know how to write the sample space and so on and so forth. But this example fits into this scheme of product probability spaces. Is that clear? I hope. Yeah. So it is in this sense that we are saying this. Okay. Of course, you will see later on many examples where omega 1, omega 2 can be subsets of real numbers, or maybe even more general. All right. Yes.
So what if we say that omega 1 is the set of outcomes of the first time you toss a coin? And omega 2 is also the set of outcomes of the first time you toss a coin. Does anything prevent that?
Then, okay, so are we looking at product spaces or no? See, omega 1 equal to omega 2 here, you see, omega 1 is equal to omega 2. But the moment you talk omega 1 cross omega 2, okay, of course, this is same thing as omega 1 cross omega 1. There is absolutely no difference because they are the same sets after all, right? But what do you mean by, now tell me, what do you mean by omega 1 first time and omega 2 second time? Omega 1 second time are independent. The only way I can make sense of is if you say, but why omega 1? So A can be anything, any subset of omega 1, and B can be any subset of omega 2. Then I am saying A cross, this is exactly what I could have written T here. I said that actually. This and omega 1 cross B are independent. This is what I was saying. You can put whatever you like. You can put omega 1 and then you can put, okay, you can put omega 1 here and this is also omega 1 in the previous example because they are the same. It doesn't really matter. What you are constraining is only the first coordinate in this set. What you are constraining, the second coordinate is only this set. They could, even A can equal A. B and A can be equal, like in here. Okay? I deliberately wrote here H. Yeah. So if you like, you want to be very rigorous, I have to put it in curly brackets. These can be, yeah. Think about it. I hope it's not confusing the way I'm saying it. It's a very simple concept. You already know it. So you toss a coin 10 times. The occurrence of head in the ith toss is independent of the event that the jth toss results in this one. When you write this results in head, whatever. So when you write this as an event, okay, so the number of favorable events you will write. I am only telling you the ith toss, okay, is head. We have seen examples like this before. Because there it was all discrete probability, you could write everything. But here we are doing things in a slightly more general situation. It's exactly like that, no different. Okay. What the only subtlety I have gone through it maybe more than once. This condition, so which I have elaborated on already. Otherwise, it's all very clear, I hope. Okay.
Sir, I have a question.
Hmm.
Could you please scroll to the place where you have defined G set, like G of?
Yeah, sure. Okay, no problem. Yeah, here.
Yeah.
Intersection of all sigma rings of omega which contain F. This is sort of more general, not necessarily product.
Yes. So, so intersection of just all sigma ring is just omega and 5, right?
No. See,
No,
there
containing
is
F
this
is F.
additional phrase. You cannot forget that, which contain F.
Yes.
Yeah.
So my question is, so you take A1 cross A2,
Here
intersection
you
of,
cannot take M cross A2. You don't have omega here. I mean, this is
yeah,
omega
no,
here is abstract.
no, previously when you define
Previously, yes. Okay, you take you take A1 cross A2. Fine.
and here you are like, so my question is, if you take this set F1 like cross F2 and keep adding the sets which are required, like if some,
Yes.
that will, how do we know that that exactly creates the minimum sigma ring here?
Yeah. So okay, you keep on doing this, taking arbitrary union and then complementation, intersection, all kind the operations which are allowed, which are okay. When I say arbitrary, I should say countable. Yeah, that's extremely important. I keep saying. So countable union, complementation, and intersection, countable intersection, and so on. So keep on doing this. This results in a bigger and bigger collection.
Correct.
And if you can show that, so of course you cannot stop it at any finite stage. Each time you may label your operations. If you want to do things very rigorously, you may want to label your operation, and each time you label an operation, string of operations, it results in something labeled by union, intersection, complement, blah blah blah, and so on. Now you take the union of all those things, because you are only going to perform each only finite string of the thing, and then take union, and then you show that the resulting one is actually a sigma ring. Once it's a sigma ring, it has to be the smallest one, because these collections have to be there in any sigma ring. Yeah, so that's it. Okay. But it's a very complicated if you think of it, how to, because you see, there is no a number of times you can do this.
Sir, it will be a power set of.
No, it will not be. That's the main point. You take
It will be
open
subset of
intervals.
right?
You take open intervals in the real line, and as your collection, and saturate it, and you will, okay. If you assume axiom of choice, then it is not the power set of real lines. And that's a major remark, which requires some elaboration, and proof probably is beyond this course. But let me say that axiom of choice is required. You can break away with it and then do something. But anyway, so that's a different lecture altogether. Yeah. But it's easy to give examples where you may not end up with something which is power set. Yeah, I suppose. If I think of something, I'll give it as an exercise.
Okay, sir.
For instance, I think if you take F to consist only countable sets, countably infinite sets, and if your omega, yeah, but that will not be quite okay, I suppose. Anyway, let me think about it. It's rather, yeah, you, okay, if I think of something, I'll point out next time, okay? Anyway, so let's go on, what did I want to say? Yeah, I wanted to also talk about, I wanted to do some examples, is a problem. Before doing examples, completions. So I wanted to write in blue. Okay. So suppose that F, okay, let me not write F. Omega F P is a probability space. Probability space. Okay. So now once you have probability space, so you can talk about the completion of F is the sigma algebra, sigma ring generated by F union all subsets E of A in F such that probability of A equals 0. Okay, is a sigma algebra. So, okay, completion of F is the sigma algebra, sigma ring. Let me just call that F bar. Okay, by definition, this is a sigma ring. Now I write, consider, some people call sigma field what I call sigma ring. I don't know what is the, neither do I care what is the distinction. I mean, yeah. So your textbook always calls it sigma field. And I can talk about the motivation for calling this sigma ring. Maybe not now, just a little bit later, perhaps. Consider, so P, so you see now I have extended it to F bar, the extension, the X, so let me say it like this, extend P to F bar by setting P. So only you have to say what it is on the new generators. Okay, P of E equals 0, of course, for all E. So if you like, you can put tilde here, or bar here, if you like. Extend P to P bar. I should not put bar here. For all E contained in A, where P of A is 0. Not P bar of A, but P of A is 0. So you look at all subsets of null sets and throw that into your collection. And now you have a bigger collection. Of course, then you'll have to take complements also. Okay. There is a maybe better way to say it, but let me say it this way and be done with it. I don't want to waste too much time on this one. And this process is in fact important, particularly when you have again arbitrary, F omega. So and F is some large collection and so on. Okay, so this is important to have. Okay, so it's like when you have a null set, and if you have a subset of a null set by definition is something for which probability of A is 0, and that automatically means that A is already in your F. But it could so happen that A is in your F, but E, which is a subset, may not be there. So one consequence is that suppose that, so this is a remark, so A is contained in B and A and B are in F, we are in F, and probability of A is equal to probability of B. And if so A contains E, A is contained in E, and E is contained in B, then B is in, sorry, not B, B already is there. So E is in F bar. So a trivial thing to prove, I will leave it as an exercise for you to do it. Okay. I have nothing more to say about this completion for now, but it's an important property to have. Okay. Now I want to do some exercises, both from the book and some comments and so on. Let me do this. So, example. Okay. So suppose that A1 are in F. So show that this is called Boole's inequality. Show that probability of A1 union AN is less than this sum of probability of AK, K going from 1 to N. Okay. So I'll just leave this proof to you, but only one comment. Proof is by induction. Okay. So let me now do a problem. So here is an example or exercise. Suppose that so you can use probability in many situations. That 10% of of a sphere of the surface of sphere or painted blue. This is from the book, okay? And remaining 90% is painted red, let us say. Sorry. Okay. Show that one can inscribe sphere. Inscribe a cube in the sphere. Sorry about that. The sphere such that all its vertices are in the red region. So you are not told which 10%, okay? That you some 10% of the area of, if you like, area of the surface sphere. So, if it is all confined to just one small portion or something, 10% connected or whatever, then it's okay. But it may just so happen that this is even a disconnected region, spread in some varying shapes and so on. And then it's not clear that you can place the vertices of a cube in such a manner that all its vertices are only in the red region, none in the blue region. Okay. So the main thing is, so it's difficult for me to inscribe the cube in a sphere, so I just draw the cube. Okay. So the thing is, so let us just label this A, B, C, D, hardly visible, E, F, G, H. So probability that A is in the blue region. Okay. We want A to be in the red region. So any one of them. So okay, probability. So okay. Let E. So I could have labeled this 1, 2, 3, 4. E of X be the region. Event that the vertex X, call it X, is in blue. So what is the probability that one of them, probability that, so E of A union E of B. Okay, let me write here without probability. E of A union E of H is the event. I can call this my E is the event that at least one of the vertices is in blue. What is the probability that this happens? Then probability of E is equal to probability of this EA, EH. Well, by Boole's, this is less than or equal to sum over. I wish I had called it numbered it instead of giving it letters. There are 8 vertices, right? And each one of them belongs to the same region. And so this is 1/10 plus 1/10, 8 times. So this is equal to 8 by 10. Therefore, probability of E complement is 2 by 10, which is positive. Therefore, it is possible. It is possible. With a positive probability, yeah. So, you choose. So you see, if this was, if
Sir,
the
shouldn't
task
we
was
be
impossible, yeah.
probability of E complement greater than equals to 2 by 10?
Yeah. Sorry. Yes. Of course. Okay. So if it was impossible to place a cube like that, then probability of E complement would have been 0. Okay. Therefore, it is possible to inscribe the cube.
Sir, but there is a difference between null event and impossible event, right? There is a difference between null event and impossible event. So,
Huh. Yeah, if it is an impossible event, that means we are talking about empty set. Okay.
if the probability is zero, we
Yeah,
cannot.
probability is zero. Of course, probability is zero doesn't mean it's an impossible event. Probability, I mean, but you want to say that it is possible, right? You want to say it is possible. You show that the probability is positive. Okay.
Yes, sir.
Yeah, that's all. All vertices in red.
So even if probability is zero, it won't prove that it is impossible, right? Like it can
Yes.
still happen, right?
Oh, yes, of course.
Okay.
You see, it's enough if you just choose 8 points, okay, to place your this thing. And suppose my region, suppose my okay, just it's unfortunate that I chose all these labeled by letters. You see, I could have just said that let me call this R. R is the, after I place the cube, I get only 8 points. Okay, is the set A1, A, B, C, blah blah blah, H. Then what is the probability of uh, the some random points landing in this set are that 0. Okay, because here the hidden, what I did not explain, the assumption is that probability of choosing a random point in a blue region is the same as the proportion of the blue region, area of the blue region to the area of the sphere. That is 1 by 10. Okay. What is the proportion of the area of 8 points? Okay. In the to the total area of the sphere, 8 points, 0, because point have no area, right? But these are conveniently, I mean, strategically chosen points. So if my set, I mean, if I could have just had my region to be my just 8 vertices is enough. I just choose those 8 vertices, and then I don't care what happens to the rest. Then you see, I am able to plot my position, my cube, because that's how I chose my points in the first place, after all. Okay. Okay, so probability being 0 doesn't mean that it is an impossible event. Here is an example. If you want a simpler example, I can just show you. Maybe that is much easier for you to follow. So I just choose my points. This time I will conveniently call it this unit circle 1, I, -1, and minus I. Okay, and my set R is just this, or I'll call it S. S is equal to 1 minus 1, I minus I. What is the probability of choosing S in the circle? You think, of course, this is a unit circle. So what is this happening? This is 0. Okay, but one can inscribe a square with vertices on S. Yes. So although this is 0, this task is still very much possible. You understand?
Yes, sir.
Yeah. Okay. So let me proceed further. Always it's a race against time. I have written down some nice exercises. Here is a nice exercise. I'll just say it. Okay. Using probability exercise. using probabilistic methods. That's a correct word. Let's say probability. Okay, let me write. Methods show that if 0 less than A less than capital A, then 1 plus, things written here I have to write carefully, A minus A by A minus 1 plus A minus A times A minus 1 minus A divided by A minus 1 times A minus 2 plus blah 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 plus the last one is A minus A 2 1 divided by A minus 1. How many factors are there? A factors. I go all the way up to A, and this is equal to 1. No. This is equal to capital A by small a. Okay. And capital A is a bigger number. So there's a hint given. Without this hint, it's difficult to come up with some nice thing. But perhaps it is very much possible to come up with a story which will fit into probability theory and whose calculation ultimately will lead you to this identity. The thing is, I don't like this capital A by small a because this is some number bigger than 1 and we would like to have it actually equal to 1. Yeah. So how do I do that? I just put equal to 1 and then multiply by the reciprocal of this. Then I will have A by A. So this is equivalent to A by A plus A times A minus A divided by A times A minus 1 plus A by A here A minus A blah blah blah. Okay, so I'm writing a general term here, but working with specific term. A minus 1 minus A divided by A minus 1, A minus 2, blah blah blah. I know it will end at some finite stage. Okay, so this is equal to A, equal to 1. So now here is a hint. So the thing is, you interpret each one of these as probability of something or the other occurring. Okay, and of course this is a last term. There will be a term coming in here, corresponding to this, but I'm just going to leave that. Okay, so I'm not going to write that. So so here is the story that will lead to this answer. Okay, so suppose an urn contains A balls of which small a are red. The remaining, it doesn't matter what color they are, the remaining are blue. Okay. What is the probability? So I didn't say it properly. Before saying or asking for probability, I should say what the experiment is. You draw one ball at a time without replacement. Okay. Let AR be the event that the first red ball is drawn at the rth draw. Now I say what? Find P of AR. Okay. So what is P of A1? Let us do this. So P of A1 is equal to, well, there are A balls, red balls, from a capital A total number of balls, and the first ball that you draw is red already. So it has to be A by capital A. Probability of A2. So the first ball drawn has to be blue. And how many ways are there of doing it? Okay. So there are A minus 1 small a blue balls and divided by
Capital.
A, and then A by A minus 1. Yeah, and so on. So let us do it one more time. What is A3? The third ball drawn is red. That's the first time a red ball had been drawn. Okay, so A minus A. After you draw a red ball, a blue ball, you will have only A minus 1 blue balls, and in the denominator you should have A minus 1, and then the third time a red ball has been drawn. So how many ways are doing that? A by A minus 2. Okay, now you complete. So now you see you are generating. So you see first this is probability of A1, probability of A2, blah blah blah. Okay. Okay. Of course, if you just this process, you cannot go on indefinitely. Probability of last time. See, you will once you exhaust all the blue balls, the next one that you draw will have to be red. So when will you exhaust all this thing? A minus A, I suppose. So this A and this A gets as a clash, but I hope you understand. I should have called it E1 and E2 and so on. But anyway, so you do this. After this many, I think we will have the last time. This probability of this happening will be A minus A, A minus A minus. It will go on like this and divided by. So I think it has to end with 1, but just check that. Here A minus 1, A minus 2, A minus A. So no, it will have A minus A. That will be A of them, and then A by A. Sorry, so A by whatever it is. A minus A plus 1, I suppose. I don't know. So just check this. I may be off by. So this is for you to check. I told you. This should match with the last term in that series. Okay. A minus A. So it always starts with A minus A. It keeps going down all the way up to 1. Without this A and this A are paired. Okay. So you go all the way up to A. From A minus 1 up to A. So that's what you have. So this term is correct. And this one, it must be the very first term that maybe this is not there, I think. Maybe there's I'm off by 1 here, I don't know, just so probability of this after you have exhausted this as the first one, I can put A equals 2 and then check that. A equals, there's a plus 1 here for sure, yes. So you see here I have A minus 2 that came from A minus 3 plus 1. So this one, A minus A plus 2 maybe. Check this. And then this one. Yeah, this is the right one, it should be. After you have drawn A balls, so this must be A minus A. So this one should not be there. So, but here there is a 1. So just erase this once again, write it properly. A minus 1, A minus 2, there are 8 terms. Blue color. A minus A plus 1. And then here A minus A. You have drawn A balls already. A minus A balls. There must be a plus 1, I don't know. Anyway, please check this. I'm not very good at this. So I struggle. Should be exactly the last term of that one. A minus A. Oh, sorry. This is, there was an A here, A minus. I keep making mistakes. This was right. A minus A, which is correct what I wrote. This one, what should it be? You have already drawn A minus A balls. What remains must be what you should write here. And that is A minus A. So A minus A, I think that is correct, A minus A. No, there is a plus 1 here. And this is A minus 1. I think this is okay. This must be perfectly okay. Yeah, check this. So I'll put a question mark. I think this time I got it right, but please check. Okay. Now it is clear. That's it. Beyond that, you don't have to go, because after A minus A plus 1, your maximum value for R is just this number A minus A plus 1. Okay. And now this identity is simply a consequence of this identity. This says that sum of the probabilities, because these are all pairwise disjoint, this is saying that probability of A1 union blah 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 union A So A minus A, one more time, I think one ball, A minus A minus 1. How many am I drawing? Minus 1 plus 1. Yeah, if I draw this many, probability is 1. That's exactly what this is saying. Okay, that's exactly. So you just add up all these probabilities, you get 1. And that is equivalent to the given identity. Sorry, it took some time, but do I want to discuss any more problem? There are many things I wanted to say, but okay, quickly, I will do this following thing. It's an important notion, so let me do this. This is also given as an exercise in the book. So what exercise? Okay. Suppose that AN, this will go really fast. Suppose AN is a sequence of events. Is a sequence of events. And that means each AN is in F. Yeah. Let so Bn is the event that you are looking at. AM, M is bigger than or equal to N. And you are taking union of all these. So, and Cn is the event intersection of AM, M bigger than or equal to N. Okay. Note that. So, note. So you see, AN is caught between two things. And let me write here Bn plus 1. No, I should write here in contained in Bn minus 1. It contains, okay, let me write this. Cn, this is easy. The next one is also easy. And this is true for all n. For all n, this happens. And these Bn's and Cn's are nested. Okay. So, which way? So, Bn plus 1 is contained in Bn. Okay. B1 is the biggest of them all. And Cn has just the opposite behavior. C1 is contained in C2, contained in blah, blah, blah. Cn. Contained in Cn plus 1. Because they are taking intersection over smaller things. Okay. All right. So if I write, therefore, I may write here Bn. Okay, what is the question? Let me write the questions before I can start on this one. So these are observations, questions. Yeah. First of all, before even asking the question, so it makes sense to talk about, so show that intersection Bn, which we will call B, and union of Cn's, which we will call C, okay, or events are in F. So this is the first subdivision. So notation is that we say that B is equal to lim sup An and C is equal to lim inf of the sets An And B is then you have an explicit description for B. B is equal to set of all x in omega such that x occurs in infinitely many a case. So it occurs in AK for infinitely many values of K, AK, K. And C is the set x in omega such that x occurs in AK for all K, for all but finitely many values of K. Okay. We say that lim an is equal to A if B equals C equals A. The common thing you just call it A, and then if this happens, then you just say limit n going to infinity if you like. An is equal to A. Okay? So show that suppose if limit n going to infinity, an, mind you, ans are sets, they're not numbers, then probability of A is equal to probability of, okay, limit n going to infinity, probability of an. Okay, so I wanted to do many more things, but didn't have time. What I suggest is the following. So it's clear that B and C are events because you see each Bn is an event because it's an intersection of Bn is a union of certain events, countable union, and this is a countable intersection, and therefore B and likewise C are events. Okay, now this is why. So you have two things to prove. Suppose X occurs in infinitely many AKs. Okay, what does that mean? So if X occurs in infinitely many, is saying, then notice that X occurs in Bn for every n. Okay, no matter how large your little n is, there is a bigger value of m in which your X appears. Okay, such that in AM that value of X appears, that element X, and that shows that X is in Bn for every n. Therefore, okay, this set is contained in here. Now you take any element of B. What does that mean? That is in every Bn for each n, and that means that that element has to occur infinitely many often, because if it doesn't, suppose it occurs only infinitely many, now say capital N, from B capital N plus 1 onwards, it will never occur. And so that is the proof that this holds. So this also you have verified. And likewise C, I mean, C, entirely analogous proofs. And what about this? You just have to play around with inequalities. Okay, so, and I leave that to you as an exercise, but please try this exercise. The crucial point is that because, yeah, so note that since B is equal to union of Bn, sorry, intersection of Bn, intersection of Bn, and C is equal, I'll stop in 1 minute, okay? Sorry about that, exceeded time limit. Cn, limit n going to infinity, probability of Bn is equal to probability of B. These are actually also nested here, but anyway, so that is used. And here probability of C is equal to limit n going to infinity, probability of Cn. And from that, you can prove this. So let me stop here. I was very fast about this. I'll stop here because I already exceeded time limit. Okay. See you on Wednesday. Okay. Yeah.
Thank you, sir.
You're welcome. You're welcome.
Yes, sir.